Morning, everyone. My name is Thiagu. I am a Senior Applications Engineer with TriStar, and let me welcome you all to the TriStar webinar series. Today's topic is going to be on Creo Simulate. Just wanted to cover a few topics on Creo Simulate in the next 30 minutes or so. Before we go over the agenda real quick, I wanted to just remind you about the time-limited offer that TriStar is running a promotion through the end of this month on Creo products that are 40% off. So please reach out to your account reps at TriStar if you need more information regarding this time-limited offer. Also, if you're interested in any type of training, PTC standard training or custom training, if you'd like to find a course near you, please check our website that has a list of certified training courses, or you can also do virtual training. So with that said, just from an agenda standpoint, some of you may have used Creo Simulate, some of you may not have used Creo Simulate. So I wanted to just quickly cover what exactly is Simulate, what are its capabilities, right? It's scalable, as you know, from basic part analysis to assembly analysis, all the way to vibration studies and thermal analysis. I also wanted to go over the key technology difference between Creo Simulate and a traditional analysis tool. Now, all of you will be muted during this presentation, but please feel free to type in your questions at the bottom in the chat session. And after about 30-35 minutes, once I'm done with the presentation, I will try my best to answer all the questions that comes through in the chat session. So real quick, I'm sure many of you know and understand the advantage of doing simulation early in the design. Whether you're a design engineer or a mechanical engineer or product development engineer, you know that early decisions have a huge impact, and you could see the proof right there on the development costs, warranty costs, the ECUs done, how much ECUs are done after a design release. So that's one of the big advantages of using Creo Simulate, and that is integrated to Creo Parametric, right? As you're working on your design, you're not going to spend a lot of time on the pre-processing side of like a typical analysis tool, but you're still able to get some good, accurate results based on which you're able to make some good engineering decisions, right, on your designs and improve the performance of your design, wherein you have your Creo dimensions and parameters, and you can quickly run what-if scenarios to help you through that decision-making process rather than doing trial and error or over-designing it, right? So most of you know the current status of the Creo family apps, right? That's what we see here. Creo Parametric, what you're currently using as your design tool. Creo Simulate is the simulation tool, and it can work in conjunction with Creo Parametric as an integrated extension, or it can also work as a standalone app. So let's say you have analysis groups that would work only in analysis. You can just install Creo Simulate separately, so you're not using the Creo Parametric app or you're not using the Creo license itself while doing the analysis, right? You could use it licensed when you do kind of like a what-if scenario, or when you're running some optimization studies, you could make use of that, but you do have the option to just run a standalone simulation app instead of running it in the integrated mode. So what exactly is Creo Simulate? It's essentially PTC's computer-aided engineering tool, right? So that allows both structural and thermal simulation. And like I said, you can just open up your parts, assemblies, and simply access Creo Simulate from within Creo Parametric, or you can just run it as an independent application, right? The advantage of running it as an independent application is you're not locking down a license of Creo Parametric while using Creo Simulate, right? That's really the difference there. Or you may have analysis groups, right, that just do analysis, or you may be using even a different CAD system other than Creo Parametric. You could just use Creo Simulate and bring in non-CAD, non-Creo data into Creo Simulate, right, including neutral files like step and IGES files, and if it's a solid model, then you can run the analysis on that. Now, as for a learning curve standpoint, Creo Simulate looks very much similar to Creo Parametric from a usability standpoint. You see, I'm sure all of you are by now used to the Creo Parametric ribbon UI. So Creo Simulate has the same ribbon interface. So depending on, are you going to be doing a structural simulation or a thermal simulation, right? Depending on that, your loads and boundary conditions obviously are going to vary, and you can just straight away set up your model and run a quick analysis, or maybe you want to use some advanced options in assemblies wherein you might want to add a contact interface, or you might want to add a weld, or you might want to add a fastener with preload, and you want to check the load path through the fastener, right? So things like that for advanced options, they're all under this one single interface, as you can see here, the refine model, the home tab. That's pretty much what you'll be using it for, right? From a licensing standpoint, just wanted to quickly touch on the different license options available for Creo Simulate, right? If anyone that has Creo Parametric, you are able to run a basic analysis, like a static analysis, on any part or assembly that has less than 200 surfaces without any add-on license. That's the Creo Simulate Lite, right? So as soon as you launch Creo, you open up your model, take it to Simulate, and can turn on the Simulate Lite, which allows you to just run the analysis using a guided interface. And then there is also Simulate Alive if you have the Creo Essentials Premium that's bundled into Creo. And then Creo Simulate functionalities are bundled into that package, wherein it allows a few more additional capabilities compared to the Lite. And then you have the full Creo Simulate basic license extension and the advanced extension, depending on if you need vibration studies, nonlinear analyses, right, nonlinear material properties, etc. There's also a fatigue advisor extension that can sit on top of either Creo Simulate extension or advanced Creo Simulate that allows you to do durability studies, right? It gives you the confidence of life, essentially, telling you that what is the chance, after how many cycles of loading am I going to see a crack? When will a crack start to grow? That's what it's going to give you. Very basic fatigue analysis, which requires a static analysis as a reference analysis. So this comparison matrix might help you kind of understand the different packaging here, just so that you are aware. The light, the first column there, allowing parts and assembly static analysis, but the number of surfaces, right, are limited to 200 surfaces. Once you go beyond that, let's say your model has more than 200 surface count, that's when you have to go through the other columns there, which is the Essentials Premium, allowing you to do some design optimization, which is huge, right? Especially when you're an engineer or a designer, you don't want to pass the model back to an analyst. Change the design, go back to the analyst and say, rerun it for me. You want to do it automatically from within Creo Parametric and Creo Simulate environment as they're integrated. So you can really run those what-if scenarios that are very helpful to make those decisions, right? I want to minimize the weight. I want to make sure the stress deflection or the model frequency, right, or even the temperature when I'm doing a thermal analysis should be less than a certain value, and I can give a solution space, which is my design dimensions that you use for modeling your design in Creo, and you can use that solution space to achieve an optimum design, right? Now, depending on if you need nonlinear analysis, large deformation, dynamic, or transient thermal analysis, depending on that would, you could go with the advanced Simulate extension or just the Simulate extension. Used to be called formerly Basic Mechanica and Advanced Mechanica, right? And on top of these, you have the Creo Fatigue Advisor extension that quickly gives you, right, it gives you the confidence of life. It'll tell you at what and how many cycles, is there a chance for crack to start, right? The piston there, right, and I'm going to apply a static load, but I'm going to apply it or I can give it the endurance limit, right? I can specify the cycles, and it's going to tell me, right, within that cycle, is there a chance of a crack to start, right? Not the dynamic crack growth, but just it's going to tell you that's what you would be interested in most of the time, if there is a chance of a crack to start due to fatigue, right? Due to metal fatigue mainly. So one quick thing before I show you some examples, I wanted to go over the simulation technology as to how it is different from the traditional or the conventional analysis technology, right? Or the FEA technology that you might have heard of. The traditional method, as you know, is very much dependent on the user's experience, as well as the mesh density. How much are you refining the mesh? The more refinement you get, the accuracy is better, as you can see that example there, right? With the cantilever beam situation, higher the degrees of freedom or higher the mesh density, I'm a lot more closer to my hand-calculated result that I have there, right, for that particular beam size, the maximum deflection and the maximum stress. However, in the real world, when you work on a lot more complex geometry, right, first of all, you're not able to do a hand-calculated result like this, and also how much time are you willing to spend on the pre-processing, right? You may not be experienced in FEA to have to kind of automatically tell that, okay, I need so many elements for this aspect ratio, right? I need so much of a mesh density for this aspect ratio. So instead of using the H method, Creo Simulate uses the P method. P stands for polynomial, wherein instead of mesh refinement, the P solver of Creo Simulate automatically increases the polynomial order of the equations used to solve for deflections and stresses. Now, this is huge, right? So if I have a plate with a hole, do I just go with 1,000 elements, mesh tetrahedrons, or shells, right? Or do I go with 100,000 of them? How do I determine that, right? So that's something that comes with experience in the traditional FEA tool. However, in Creo Simulate, as you can see on the right-hand side, all it's using is 4 shell elements, and it's able to achieve convergence because it goes up to the 9th order polynomial. So we are essentially transferring the burden of getting accurate answer from the user's experience to the software's adaptive solution, right? So this is huge because, being designers, you want to focus on your design and run a quick analysis. At the same time, it needs to be accurate, right? And you don't want to spend a lot of time pre-processing, controlling the mesh, defining which mesh type you want to use. Now, when you get into advanced analysis, like assembly level analysis with contact, large deformation, or you're using elastoplastic material properties, that's when you might have to refine the mesh in Creo Simulate as well, which can be done. So it does allow mesh refinement but from the get-go, you want to take advantage of the 9th order polynomial for solution convergence, right? Here's an example. It really starts off with a linear equation. So the graph that you see on the right-hand side could be stress or deflection on the y-axis, and on the x-axis could be the number of passes it's taking, for getting that accurate solution. So in the second pass, it uses a linear equation, right, and it solves for stresses and deflection. It will see the difference between the two, right, between the first pass and the second pass. And if that difference is less than a user-defined percentage, it'll tell you that's your answer, right? So you're essentially controlling the accuracy. If not, it keeps bumping it up to the cubic equation, 4th order equation, 5th order, all the way up to the 9th order. So you can see the graph that you see here. I'm a lot confident now that my solution is accurate, right? So rather than looking at a cool color plot and saying, hey, those red areas are the high stress areas, and then saying that's accurate, it's very important to make sure you check the convergence of solutions in any analysis tool that you use, right? So this is adaptive. And it's not dependent on the user's experience, right? So that's a key technology differentiator between Creo Simulate and many of the other analysis tools out there. Here is a case study wherein a turbine blade was analyzed using the traditional FEA method, wherein, as you can see, for about 3,000 elements, I'm getting a maximum stress of 400 odd psi. And then if I bump it up or if I double it, see the stress keeps increasing or changing as I increase the mesh density. So this pre-processing time and the effort is what we want to avoid using the P method, wherein it just maps the geometry as is. You're not approximating the elements, right? And it runs it in much faster time because we are not manually doing any type of mesh refinement. The software essentially elevates those polynomials and it's giving you the maximum stress there, right? So I'll show you with an example on this accuracy thing because it's very important, even if you're currently using Creo Simulate, to make sure you plot those P loops or the P graphs for stresses or deflection, strain energy, so you know that your solution is accurate and you can start making some engineering decisions based on that solution or maybe make some improvements based on that report that you got from Creo Simulate. So with that said, let me just spend the rest of the time with a few examples here. I wanted to quickly show in the next 15-20 minutes here. I have assemblies and parts, but let me start off with an example of an assembly. So the assembly that I have here is a pretty straightforward, simple part, as you can see here, and it's a Creo assembly. And let me redefine this assembly. And when I redefine this assembly, let me just go and disable my coincident constraint. And my goal here is to analyze pushing this part with a certain force. And I do want to see the contact in here, right? I know that this surface might come into contact and that surface is going to get pushed up a little bit, right? And there might be large deformation. There's going to be contact stresses, forces working here, right? So such kind of assembly analysis can also be easily and quickly to be set up in Creo Simulate, right? So rather than thinking Creo Simulate as only simple part level analysis, please remember you can use really large assemblies with large deformation, with contact, with interfaces defined. You can even define welds in assemblies, right? So in this case, what I'm going to do is I'm going to take this assembly as is to simulate. And when I take it to simulate, obviously I'll be applying the material properties to it, but to make sure that this part is pushed inside, I can either apply a force if I know, or I can simply assign a enforced deflection. Actually, it's a good practice to apply enforced deflection instead of a force for a situation like this, right? For snap fit assemblies, things like that, you're really not sure by how much force you're pushing it with, but you know you're pushing it and it has to go deflect or it has to go travel a certain distance, and that's what you'll be applying here essentially, right? So I can just say in the Z direction, I'm able to apply a certain value, right? So I can always go to my analysis here, and I could just measure the distance between this surface and the surface, right? And I can simply use that, right? I could essentially just use that guy right there, and I could put it in my constraint as an enforced deflection. It's a negative value, right? Very good. So I essentially want the software to calculate the force required to push it that distance. I can add a measure. That's something that it can report, but the main thing is that I don't know. Am I pushing it with 5 newtons, 10 newtons? I don't know. I just know by how much it's being pushed, right? So I'm just applying an enforced deflection to that surface, really, right? And I want to also constrain this part. And I can go to my material properties. And you can customize these material properties. It's pretty much the same that you get in Creo Parametric, right? And you can assign the material properties. And once you do that, right now I can run the analysis. However, this part, the yellow part, will keep flying away because it doesn't know where to stop. I've not defined an interface, right? The default behavior in Creo Parametric is it's bonded. If two surfaces are touching, it's bonded. And here, we don't want to have a bonded functionality here, right? We want to have a behavior wherein the surfaces slide against each other or push against each other. So in such situations, I could add an interface. I can either detect interface automatically, contact between components, or in a component like this, it may pick up so many surfaces that may not even come into contact. So I can manually define the contact pairs, right? I can just say that's a surface, right? And I have the ability to add infinite friction or even finite friction, right? Once I define the contact, I'm essentially copy pasting that, and I'm going to say my second reference could be this surface as well, right? So like this, I'm just going to start creating so you can see my contact pair definition right there. And I could say, let's just define a contact pair between this surface and this, right? So once it goes beyond this, it's going to come in. So all the surfaces that you feel might come into contact, that's pretty much what you're doing here. And once you define the contact, you can pretty much define the analysis here as a static. It's still a static analysis, and you can have it use large deformation with contact. So you can see how it automatically picks up the nonlinear option since I have contact analysis there, right? So really no loads, just constraint will act as a load that enforces deformation. And I can just go into my output and say I just want to have user-defined outputs, and I want to see this in steps. It's almost like simulating the load in steps there, and I could say I want to have about close to 100 steps here. I'm going to space it equally. It's essentially giving a percentage to the load. So I can, once you run the analysis and during the results, you're able to track at each step, right? So that's the advantage of adding this. So when you do this type of a static analysis, and if I were to go to my results here, these are the steps that I've added, right? And I'm interested in the stress plot. I want to just show the deformed model with 1:1 scale and animate it. So right now what it's doing is it's really going through those steps that we defined. There you go. Right. Let me just go to my animation speed and increase that. So you can see how the contact pairs, right? We're pushing the surface, and because of the contact definition on either side, I had defined it on either side, right? For the two tabs in here, you can see, this is where, you want to check this, if this maximum stress has gone beyond yield for that material. Could be improve this design, right? What changes should we be making in this design, right? Could be add a fillet in there, right, to help reduce the stress, etc., right? So that's just to show you an example of a large deformation with contact in an assembly like this. But you're thinking sometimes you just want to do simple, basic part level analysis using Creo Simulate. You can do that too, right? It's not that you have to do only assembly. You can just do basic part level analysis as well. So let's say I open up one of the very simple parts here, and let's say the situation here is, if I were to go to my front view, the situation here is I have some of the part coming in here that's attached to it or bolted to it. For example, I apply a load here, and I want to really analyze the bracket. And I want to know, not only simply analyze it, I want to maintain the function of the bracket, right? Could the bracket look like this, for example, right? Could we have an angle here? So I want to optimize the design based on my analysis reports, right? So just to run the what-if scenarios as well. And so what I'm going to do is let me just go to Simulate, and I'm going to simply assign a standard material here. And let me constrain it at the top and the bottom here. I'm going to fully constrain it, assuming that's welded, right? So it cannot move in XYZ, cannot translate in XYZ. And different loading options, right? Force, moments, bearing load, etc., right? So since the cylindrical geometry, it would be a bearing load here. Just going to apply. And then again, the unit system, you can change it anytime. It's regardless of the unit system you have in your model. You could change the unit system. Same thing with reporting, right? Do you want to report the stress in PSI or megapascal? It doesn't matter, right? Similarly, I want to add a bearing load to the bottom. There it goes. And I can technically run this analysis. Now, remember, as I was talking about that technology where it automatically creates the mesh and elevates the polynomial. So I don't even have to really create the mesh. I mean, if I have to look at the mesh, I can, right? I can go and say, let me just create the mesh, and it will create the mesh for you, and you can see it creates a tetrahedron mesh, and you might be surprised as to how big of an element it's creating around the holes and curved geometry. It is not refining it in here. The reason it goes to a 9-powder polynomial automatically, right? You have some mesh control options where you can control add a mapped mesh if you run with a nonlinear material property, for example. You can refine, you could say, I want to set up a maximum element size, things like that, but you would do that only if the solution is not converged, right? So right now I want to define an analysis, but I want to make sure it's using that multiple path adaptive solution where it goes all the way up to the 9-powder, and I control the accuracy here, right? I want to set 5% as the accuracy, or maybe let's say 10% as the accuracy, and I want the software to converge on everything. I'm interested in deflection, stresses, including strain energy, right? It's going to try to converge on everything there. And let me just, typically we recommend giving 50% of the RAM of the computer for solvers. It's a very simple part, but I could bump it up a little bit if I won't have to, since I'm running a multiple pass analysis. And as you can see, that automatic method that I showed you in the slide earlier, that's what is happening right now, where it is essentially going through those passes, right? It looks like it went through like 5 passes. And at the end of each pass, all it's trying to eliminate is it's trying to reduce the elements not converge, and its goal is to get it to 0, right? That's what it got right here. And it's telling me that it has converged. So this is the most important thing. That's the first thing I would see in an analysis, right? I have to make sure that it converged within 10%, right? Once it converged, the next step I would do is, instead of looking at the cool color plot, we should be looking at a graph. Did it converge or not, right? So I'm going to look at the measure, which is a von Mises stress, right? For a ductile material, you'll be checking at maximum von Mises, right? If it's brittle, you'll be checking principal stresses, obviously, right? Versus the number of passes, and this is telling me, right, that I have got an accurate answer right here, right? It's telling me how the stress is approaching a certain value. It's within that 10% that I asked for, right? And similarly, I'm going to say the same thing I want to do with the maximum deflection magnitude. There is my displacement in the y-axis, with the number of passes. I'm going to copy that and say, let's also plot the strain energy right here, right? So after this tells me that it's accurate, and now I can go and plot the P level. So the P level is telling me, right, essentially showing me the mesh, and it's telling me none of them are in red, meaning none of them reach the 9-powder polynomial or the limit of the software. So it looks like, you see here I have the maximum level reached the 6th order, which I'm happy with, right? That's telling me it's an accurate solution. Or I can just go and edit that fringe plot to a stress plot, right? I can also set it to, I'm just double-clicking it, and you see in Creo 3, the interface in Creo Simulate is really improved, where it's just very ribbon UI based, just like the other applications in Creo. I'm able to animate this, and there it goes, right? Now, let's say the stress I got, the maximum stress I got is 140, but I'd like to further reduce it. It should be less than 100, or I need a factor of safety, for example. What I could do is I could run those what-if scenarios. I just asked the system how much questions, and it answered me that, right? The maximum stress, maximum deflection, what have you. Now what I could do, I could say I want to do an optimization study wherein I'm essentially going to tell, okay, this part in a mass production scenario, right, I'm worried about material costs and I don't want to over-design, right? During my industry days, I've done that. I'm guilty of that too. We all over-design, right? But it could be reduce the thickness, could be just save on material costs. I could say minimize the mass and make sure your maximum stress, right? I can just say the maximum von Mises stress should be less than, let's say, so much megapascal. Now, I came up with this number by giving a factor of safety to the yield, right? You know, so I get roughly like 2, right? 2 or 2.5 is the factor of safety I gave here. And the same thing, I can say maximum displacement magnitude as well, right? I want to add that, and I want to say the maximum displacement magnitude should be less than so much millimeters. So these are kind of my design limits or analysis solution output limits I'm going to give the software, and I need to give it a solution to work with, right? A solution space, essentially. So I go to my dimensions, I can essentially select my Creo feature, right? I'm just looking at the radius. It's from, you know, let's say the initial one, let's say it's 2, it has to go all the way to 12, right? Let's say as an engineer, I know that's the limit we have on the design side, and give me the best possible solution. So like this, I could pretty much select my sketch, my base sketch feature, right, that I use. I could use an angle. I could use that upper length. I could use the length at the bottom here. I could use a width, etc. So like this, I could use any number of dimensions, including pattern dimensions. In assemblies, imagine you have a flange with bolt holes on it with fasteners. I could even use a pattern of the holes. So when I change that, the number of bolts change. See the analysis update. So this really, you know, one of the big advantages of using Simulate inside of Creo Parametric, right? You're able to run the what-if scenarios in there. And once you run this, what you're going to get out of an optimization result is, if I go to my optimized model, the first thing you're going to see is, obviously, I need to see the graph of the measure, right? I asked it to minimize the mass, so let's look at the mass versus the number of passes. And as you can see, it reduced the weight. I'm also going to copy that graph, and I'm going to plot the max stress von Mises. And you see how it has also improved. I mean, it has reduced the stress compared to what it was in the initial design state that we gave. And I also want to plot the maximum displacement, right, or the deflection magnitude, maximum deformation, because a small deflection of the bracket gives a large deflection at the end of the part that it's attached to, right? So I've optimized the model, and how does a new model look like? I can go look at the fringe and look at the stress plot, and there it goes. You know, you can see how it has made it a little thinner here compared to what it was before. The angle changed. Obviously, the round has been increased, and now compared to the 140 or something that I had, I'm below my factor of safety here. So this is, you know, the optimization tool is quite important, and you can do this in assemblies as well as parts. You can also do it for thermal analysis. For example, you're designing a PCB, a printed circuit board, and the CPU, the chip is overheating, and you want to make sure the temperature on the PCB shouldn't exceed a certain value. You can control that using optimization. Same with model frequencies. Same with vibration study, right? So in short amount of time, I just gave you a couple of examples here on how we can do analysis on assemblies as well as parts and do optimization. With that said, let me open up my presentation here. Let me just look at questions. If you could start typing your questions in the chat session. Let me just keep a second here. I'll just go through those. Okay. So the first question is, can the fatigue advisor take inputs from a combined thermal stress analysis to determine the maximum number of cycles a part can withstand before a user-defined failure? Yes. Starting with Creo 3.0, Simulate, before we couldn't add multiple sets, multiple load sets, but starting with Creo 3.0, the fatigue advisor, there's an improvement in there where you are able to add multiple load sets, right? So you're, for example, you could have 2 or 3 load sets, and each load set, so from a thermal, once you do the thermal analysis, as you know, you can do a structural analysis to account for the stress due to thermal expansion, right? You would add that to a separate load set, and then add that as a separate load set when you define your fatigue, and then you can go, say, 0 to peak, peak to peak, etc. So the next question, is mold flow analysis a different product, or is it an add-on to Simulate? Yeah, it's a different product. That's more for for the plastic mold. It's more for the manufacturing side, right, where you want to simulate the actual flow. Is there any air trap vents, things like that, right? So that's different. It used to be called Plastic Advisor, but PTC no longer uses that old Plastic Advisor, right? It's the mold. It's a different product starting with Creo 3.0, but that's different. It's not included. This is more simulation for performance side on just structural and thermal side, right? You're applying let's say you want to simulate conduction, convection, heat transfer, radiation, heat transfer, and you want to test the temperature, the heat flux, etc., or you want to test the stresses deflection for applied loads. That's what this Simulate does for you. Can you set up an oscillating pressure or temperature in Simulate? Is it possible to determine a combined thermal structural stress for that scenario? Yes, yes. So oscillating pressure, right? All you would do is, yes, you can, once you apply the pressure load, like I said earlier, I think Kyle, you're asking the same question pretty much. Like, yeah, you would have to add it as a load set because we couldn't do that in Creo 2. If you recollect, in Creo 3, we are able to add multiple load sets and in fatigue, right, on the fatigue side. That's how you would add an oscillating pressure, right? The next question here, is it possible to link or can link or copy of the video presentation? Absolutely, yeah. We are recording these presentations, or all our webinars are recorded. In fact, I can show you real quick here. In our website, if you go to Resource Center, CAD, Data Management, Product Development, etc., that's where we are storing our webinars. So, for example, the last webinar my coworker Sean did on using fasteners in Creo, there's a recording available. There's one on ANSYS I did before that, and all these webinars that our team does, it's going to be in our, some of them might be dated, but we are creating new seminars or new webinars. We are running almost every other week this quarter, right? I mean, starting this year, and it's there. So yeah, you will be able to access those, the entire presentation there. In Simulate 2.0, I used to have a white background saved versus my normal Simulate results window, but that seemed to go away in 3.0. It shows the same blended color background as my normal Creo. What changed here? Oh, no, nothing changed between the mic between 3.0 and 2.0, right? I mean, there are some technology improvements, right, like fastener connection, Unite technology, etc. But on the background color, all they did was, on the Simulate, the biggest change was a ribbon UI, the interface and the results, right? So all you really have to do is, do you have your config set up in such a way that it's pointing to a system color file or a syscol file that you prefer, then it should take it automatically. So I would check your Creo 3.0 after installation. Is it still pointing to the same system color file in the config that you use in Creo 2? And in that case, it should work fine. Let me just go to the next one here. if you have a structural racine, fibers in the mold racine, okay, depending upon the mold flow, the fibers may align or not, and then would have different structural properties that influence the part structural properties. Yes, absolutely. Can you simulate these direction properties of the molded part? Yes, you can. You know, the way that you do that is we do have, remember I was going over the comparisons and capabilities in Advanced Simulate. There is a way to apply direction-based properties. So it's more, when I say direction-based, you can apply non-isotropic materials, wherein in your material definition, you can assign the properties based on direction, right? You can. Now, however, with that said, you might run into situations where, like in the example that you're talking about, or it could be composites where you have multi-layered materials, you have different directions, ply thickness, etc. The way that you simulate that in Simulate is, in Creo Simulate, is using the advanced shells. There's something called advanced shells. You can define surfaces, wherein it's just like a membrane, essentially, and you are able to specify material property to each shell. So what my point is, bottom line, long story short, is you don't have to really model it, but it would be an idealization, and yes, it can be done. All right, so looks like, yeah, we pretty much covered all the questions we had. If you have any questions, please type into the chat session here. While we are waiting on that, let me just remind you one more time about those two. I think I showed this earlier in the presentation, but just a quick reminder about the time-limited offer on Creo products from TriStar through the end of this month. Okay, please reach out to your account reps at TriStar to know more about this or take advantage of this, right? And also, as for PTC certified training courses, right, we do have training locations across the country, so please check those out. You can try to look for the nearest location, or we could do an on-site training, or we can even do a virtual training course, so please check that as well. Let me just see if there is any other questions. Any other questions to chat? Okay, so it looks like that's about it. And like I showed you in our website in the Resource Center area, you could access the entire recording of these webinars. And feel free to reach out to us or let us know. There's our number and our email information there. Please let us know with any questions or comments or any specific topics in the PTC product line, right? Whether it's Creo Parametric, or whether it's MathCAD, or whether it's Windchill, PDM Link, or Project Link, etc. We would like to hear from you. So we could create topics or such webinars that will be very beneficial for you, like tips and tricks, things like that. So thanks again for all of your time, and we look forward to meeting all of you in the next webinar. Thank you.